Hello everyone and a warm welcome to Economics Pedia. Today we are here to have a look at the econometric section, and in this session we will mainly be focusing on the heteroscedasticity part. So I thought that why not to solve a past year question based on this heteroscedasticity. So here we are solving the past year I.E.S paper. I.E.S and the year is 2017. The paper you can download it from the official site. The link will be given below in the description box. So starting with question number 13, part A. It is saying that explain what you mean by the term heteroscedasticity. So we know what is heteroscedasticity is. Heteroscedasticity mainly is the violation of one of the assumptions of classical linear regression model, right? So let us consider a classical linear regression model as yi is equal to alpha beta xi plus yi. Let this be equation number 1. So we know what the terms imply. So this yi is the dependent term, xi is the independent term, and ui is the error term, and alpha and beta are the parameters. So we have classical linear regression analysis assumptions which mainly concern the error term, that is ui, right? So the first assumption goes like the expectation of ui, it has to be 0. Then followed by the variance of ui is equal to sigma square, and this is assumed to be constant. This property we know is known as the homoscedasticity. The violation of this particular assumption, when the variance of the error term is no more constant for different samples, then we have a problem of heteroscedasticity into our system. So this is the violation. This is the assumption that when it gets violated, we have a problem of heteroscedasticity, right? Okay, so let's just go through the assumptions once again. So the covariance of ui, uj is again 0. That means there will be no correlation between the error term of one sample with the other. So they will be completely independent. And of course there is again the assumption of exogeneity is there. So that implies there will be no relation between the error term and the independent term. This will be completely independent of each other. And the important assumption of the CLRM is the presence of no multicollinearity. That means as here we are considered only on this single independent variable. If we have multiple independent variable, that is known as the multiple linear regression model. For that we can say if the independent terms, that means all the x's are not dependent on each other, then we have a problem of no multicollinearity, and that is the required validation. Okay, so moving on to the definition of heteroscedasticity. So we can write it that when the assumption of variance on the error term, that is variance of ui, is no more equal to sigma square, that is constant, we have a problem of the heteroscedasticity. So what will be the variance of ui then? It can be sigma I square, that is, it is no more constant. This says the problem of heteroscedasticity. Okay, just let me give you an extra information on this, although it has not been asked, but let's discuss that as well. What will be the effect of this heteroscedasticity on this particular model of CLRM? That means when we talk about the effects, we mainly want to know that what will be the expectation, what will be the variance, and how the model will be with respect to the consistency. Okay, so these are the things we need to discuss. So in presence of heteroscedasticity, we have unbiased expectation. So it will be unbiased. Number 2 says that the model will be completely consistent even in the presence of heteroscedasticity. So the model is consistent and the third number which relates to the variance, here we are saying that in presence of this heteroscedasticity, the variance will not be the efficient one. So it will be not efficient. Okay, so what exactly we mean by not efficient? This says that the variance will be not the this says that the variance will not be the minimum variance. That means the variance will be not the minimum most that it has to be. So in that way, we have the variance to be not efficient. Okay, so this is the definition of heteroscedasticity and its effects on the particular system or model. So with this, we are done with the part A. This is question number 13. A we solved. Okay, 13A. Now let's move to the next part. 13B. Let me just read out the question for you. The question says that they have given us a model. Let's just write down the model. Beta 1, beta 2, x2i and ui. So this is the model they have provided us with, and they have mentioned that the expectation of ui square, so this is the variance of ui, right? This they have mentioned that it is sigma square xi square, and here I is from 1 to n. So they have asked us to find out the OLS and the GLS variance of the regression slope. So for this we need to know what the regression slope is. It's quite evident from the model. Let me just mark it equation number 2, okay? So here the regression slope is beta 2. So they want us to find the OLS as well as the GLS estimate of this beta 2. The estimate as well as the variance. Now, we have to look at this extra information that they have provided us with. That is, the expectation of ui square is equal to sigma square into xi square. So this xi term is there attached to it. So this implies that this variance is not constant. It is changing for every single sample, every single different sample. Okay, so here we can write that this is not constant. Okay, now let's first of all get the OLS estimate. Okay, so we get the OLS estimate by minimizing the RSS. That means the sum of the squares. That has to be minimized, and then that equation needs to be differentiated with respect to the two parameters, as here there are only two parameters. So after differentiating, we will be getting the two normal equations, and ultimately we will be getting this value, summation x2i bar, x2 bars into yi minus of y bar divided by summation x2i x2 bar whole square. Now you must be thinking that why I have not done the above steps that I have just gone through orally. So this is because, see, in the exam hall we don't have the unlimited time, right? So we have a time crunch. We need to keep in mind about that. So we cannot just forget it and write on our own. So there will be a huge amount, a great deal with respect to time and the management of it. So you have to be very much careful and rational on that part. So because of that, I'm just skipping the parts, and also the time with respect to the marks that they have provided us with, you need to be very much rational on that part as well. Anyway, so moving on, this is the value of beta 2 OLS estimate of it, right? Now let us just expand it. So here we have x2i, x2 bar, yi with a minus, and then we have y bar and summation of x2i, x2 bar, and the denominator remains as it is. x2i x2 bar, this whole square. Now I'm going to erase this part. Okay. From here we have beta 2. Now ultimately after this step we are only going to left out with this portion. That means this whole portion is going to equal to 0. Why? Because of this thing. That is summation of x2i minus x2 bar is 0. That means the deviation from the mean value is always 0. We know this property, and from that this thing is equal to 0. So ultimately we have summation of x2i x2 bar yi divided by summation of x2i x2 bar whole square. Now from equation 1 I'm going to substitute the value of yi over here. Okay, x2i x2 minus, for this you can just go back to the initial side of the video and you can just have a look from the model. I'm going to look at the question paper and write the model. So here we have beta 1 plus beta 2 x2i and ui. Yes, that's the one. And this is divided by the x2i minus x2 whole square. So the denominator remains unchanged. Now again we have to expand it, right? Let's just do that. So starting with beta 1 summation x2i x2 bar and the denominator whole square with a plus beta 2 and summation x2i x2 bar. This is multiplied by x2i divided by x2i x2 bar whole square. And finally we have the end term, that is x2i x2 bar into ui. This divided by x2i x2 bar whole square, right? After expanding, this is the thing. Okay, so from this first part, look at it. Don't we have the same pattern that we had before for the y bar thing? So here also this part is 0, and because of this, this whole term gets wiped out. And I'm just erasing this part, and we are ultimately left out with these two terms. Okay, now let's come to this side. Here I'm going to take let x2i x2 bar divided by x2i x2 bar whole square, this as something, let's say w. So here with beta 2 we have x2y attached to it, right? So we have summation of wi x2i, we can write. Okay, so here we have x2i x2 bar and x2i. Similarly for the denominator, okay, so let me just write it here. We have x2i x2 bar into x2i. Let's just expand the denominator. How? x2i x2 bar into x2i x2 bar. Multiply it. x2i x2 bar into x2i divided by x2i x2 bar into x2i. So this thing gets multiplied with it. With a minus, we have x2 bar outside and we have the original thing. So from here we can find that this thing is again equal to 0, and because of that this whole term gets 0 and this gets cancelled out. So what are we ultimately left out with? So from here, get back to here, we have x2i minus x2 bar into x2i divided by x2i minus x2 bar into x2i. So this gets cancelled out and we have the value of this thing as equal to 1. So let's write it beta 2 into 1. Okay, so what about this term? This term remains as it is. Summation x2i x2 bar into ui divided by x2i minus x2 bar whole square. So this is the value of beta 2 hat that we have obtained, right? So this is beta 2 hat. But this is not what they have asked us to find. They want us to find the variance of it, and for the variance we need the expectation value. So let's find the expectation value of it. So this is the final form for the beta 2 we have, and we are here to find the OLS estimate of it. So we can write that the expectation of beta 2 hat OLS is equal to the expectation of it. That means expectation of beta 2 plus we have summation x2i x2 bar into expectation of ui divided by x2i x2 bar whole square, isn't it? So here the expectation will be on the error term ui part, so that is why we have written it like that. Now, so expectation of beta 2 is beta 2 because it is the unbiased estimate. Now, expectation of ui, we know that assumption holds. So expectation of ui is 0 for the CLRM, and here we have it as 0. So here the expectation of beta 2 OLS hat is nothing but beta 2. So from here we can say that it is the unbiased estimate. Okay. Now, till this much we have just found the estimate. So what will be the variance of it? For the variance beta 2 hat OLS, we need the value of beta 2 hat minus expectation of beta 2 hat, this square. So we know the value of beta 2 hat, right? This was the value of beta 2 hat without the expectations, and minus of beta 2. Let's write from here. So here the expectation, what is beta 2? So this is beta 2 plus summation x2i x2 bar ui divided by x2i x2 bar whole square, and the expectation of beta 2 OLS is beta 2 again. So we can easily just cancel these two out. For the variance, we are ultimately left out with, okay, so after this we are here, that is the variance of beta 2 OLS is expectation of summation x2i x2 bar ui divided by x2i x2 bar whole square and then square whole square, right? So this is the ultimate term we have. Now we need to simplify this in order to get the variance for the OLS. Let's do that. So we have expectation, or let's just break it from the beginning. So here we have x2i x2 bar, this square because of the outer square, and then divided by summation of x2i x2 bar square, then again whole square, and finally we have expectation of ui square. So this term remains as it is. We have to focus on this term. The value of expectation of ui square was given in the beginning. The value of it is given in the question paper. It is equal to sigma square xi. So I'm just going to substitute that. So here we have sigma square xi square. This is the value of this thing, expectation of ui square. So let me just write it. So here ui square divided by summation x2i minus x2 whole square and then again square. So ultimately the final value of variance of beta 2 OLS is, we can cancel one out, and ultimately we are left out with sigma square summation of xi square divided by x2i x2 bar whole square. So this is the value of variance for the OLS estimate. Okay. So with this, the first half of 3B we are done with. Stay tuned for the next part, that is the variance of the GLS, how we are going to find the GLS estimate of it. For that stay tuned for the upcoming video. And thank you for watching this. And if you have any kind of doubts in this particular session, please feel free to let us know below in the comment section. Thank you for watching this.